Have you ever wondered why the universe seems to freeze its largest structures in place, even as galaxies race away from each other? Here's the mind-bending part. In some regions, distant galaxies that should keep accelerating beyond what we can ever see actually start to slip into a cosmic horizon. We call it a light horizon, and it feels like an event horizon, but it's not a black hole. Now add another twist. Recent clues suggest something like dark energy can make galaxy mergers stall once those mergers are already stretching the fabric of the observable distance. In other words, the universe may be reshaping the future of galaxy growth, turning a dynamic, colliding cosmos into a more isolated one before light speed even feels like a boundary. The misconception to kill is simple, that faster than light is what stops mergers. The truth is subtler. It's not that objects outrun gravity, it's that cosmic expansion changes what catching up means. And the moment you see that, the idea of a dark energy horizon stops being an abstract label and becomes a concrete prediction. To understand the before state, picture the universe when galaxies were closer together. Gravity acted like the universe's social glue. When two galaxies formed a neighboring pair, their mutual attraction could pull them together over hundreds of millions of years. Their stars and gas behave like slow dancers. Orbital decay, tidal forces, and dynamical friction gradually drained energy from their relative motion. That's how we build big galaxies from small ones. But the universe doesn't stay static. After the Big Bang, expansion slowed, then later began accelerating. Observations of distant type A supernovae revealed that acceleration, implying a mysterious energy component, dark energy that acts like a repulsive pressure on large scales. In the standard picture, dark energy is nearly uniform, filling space. Before the horizon idea fully matured in models, many discussions focused on what expansion does to the universe overall. It stretches space and dims distant light. But the deeper question was whether this large-scale acceleration also alters the fate of individual gravitational interactions, specifically galaxy mergers far beyond our local neighborhood. Here's the core mechanism. Imagine two galaxies in a vast field, like two towns connected by an invisible rubber band that can tug them together. In a non-expanding universe, if the band is strong enough, gravity from their mass, it keeps pulling them into a merger. Now replace the rubber band with cosmic space itself. Dark energy changes the shape of space over time. It makes the effective expansion rate larger, so the distance between moving points increases faster. That matters because galaxies don't move through space like boats on a river. The river is part of the stage. Their mutual pull must overcome not only their initial separation, but also the ongoing stretching of the metric between them. The concept of a dark energy horizon is essentially a scale. Beyond it, the repulsive influence associated with dark energy grows so strong that gravitational binding becomes ineffective on the timescales mergers require. Think of it as timing. A merger is not an instantaneous leap. It's a long negotiation. Even if two galaxies start with velocities that point toward each other, the universe keeps expanding the distance between them, potentially boosting their relative recession. If the expansion rate inside the region between them becomes comparable to or exceeds the rate at which gravity can draw them closer, then the inward progress stalls. They may still attract locally, forming a warped, elongated interaction, but the final coalescence becomes unlikely or delayed beyond the era we can observe. This is what stalling beyond light speed really means. The galaxies don't need to move faster than light through space to stop interacting. Instead, the changing geometry ensures that the conditions for a bound, sinking orbit disappear. There is a boundary, not of motion, but of causal influence combined with dynamical binding. Where does this come from in the evidence? Galaxy mergers are common in the early universe, when density was higher and dark energy's effect on dynamics was comparatively less dominant. As cosmic time progresses, surveys show that the merger rate drops. Part of that can be explained by the galaxies having, on average, more time to exhaust gas or by environments changing. But simulations that include dark energy suggest an additional effect. Once galaxies become separated by enough, that cosmic acceleration effectively wins against their mutual gravitational energy, merger trajectories stop converging. The term horizon emphasizes that there's a limit related to the ultimate reach of future light signals and the effective domain where bound structures can keep forming. It's not that the universe creates a literal wall. It's that expansion alters the balance sheet of forces so thoroughly that attraction can no longer close the gap efficiently. Now consider the broader implications. If dark energy can stall mergers, then the cosmic architecture of matter evolves differently than a purely gravity-driven narrative would predict. Fewer late-time mergers mean fewer new bursts of star formation triggered by collisions, and fewer transformations from disk galaxies into ellipticals via major mergers. Galaxy growth would shift from a frequent violent process into something more gradual: gas accretion, minor interactions, and secular evolution. That impacts how we interpret the observed population of galaxies at different epochs, including the abundance of massive galaxies and the shapes of galactic halos. It also changes the interpretation of gravitational wave sources from binary mergers, because the hierarchical buildup of compact object systems depends on the merger history of host galaxies. On the largest scales, this strengthens the idea that dark energy isn't just stretching light. It's shaping the ability of structures to self-organize. In principle, that lets us test dark energy's behavior. If we measure how merger rates vary with environment and distance, we can infer whether cosmic acceleration is uniform or clustering, whether it has an equation of state different from a cosmological constant, and how quickly the universe transitions from gravity-dominated assembly to expansion-limited interaction. In the modern world, these find cascade into precision cosmology. They help calibrate distance ladders, constrain parameters that affect the cosmic microwave background interpretation, and refine predictions for the fate of large-scale structure. A horizon isn't only about what we can see, it's about what the universe can still do. So here's the conclusion. We started with a misconception that only things breaking light speed cause the end of interactions. But the Dark Energy Horizon story is more subtle. It says that galaxy mergers can stall not because causality is violated, but because the geometry of space-time changes the dynamical conditions for binding. Dark energy accelerates the expansion, and beyond a certain scale, gravitational attraction loses the long-term race required to turn close encounters into coalescence. The horizon is the practical boundary where cosmic stretching outruns the sinking process. That means the universe's fate is written not only in expanding distances and redshifted light, but in the changing tempo of how galaxies build themselves. One day, enough mass will drift into isolation, and the cosmos will shift from collision-driven evolution to separation-driven quiet. If you want more on how the universe hides its rules in plain sight, subscribe for the next deep dive.